blog from OpenAI. This dates back a couple of years, so this is obviously not the latest what they're doing. But you can see that the best companies are using internally Kubernetes to scale their training and serving workloads to thousands of nodes. And scalability makes Kubernetes very attractive to launch your workflows. This slide is, or at least the image is borrowed from the amazing work on the ML, AI, and data landscape from Forcemark Capital. And it doesn't include all the MLOps tools out there, but what I did my best was to go through each of these websites and see if they are either native on Kubernetes or provide supports to it. Almost all of them provide support for Kubernetes, but the ones underlined have some sort of an implementation or way that you can use it on Kubernetes. So if you recognize any of these names, you'll know that these tools are very they like Kubernetes as well. So you're not in a bad place if you start with Kubernetes. There is this list leaves out a lot of different tools. So if you have more interest, you can Google for this awesome MLOps Git repo, which has a link to more tools. Awesome. Kubernetes, the declarative paradigm also makes it possible for tool vendors or frameworks to provide you with easier ways to deploy a model. So these are two tools that I love a lot. One is BentoML, whose Yathai release recently allows you to declare what that particular classifier needs to be deployed as. So here you can see it's an iris classifier. It has some CPU requirements, and there's also some auto scaling that BentoML is doing. Kserve also is a great tool for you to deploy your inferencing models and so on. So you can point the Triton server or K-serving container to the location of your model, and there's some predictor here as well. So amazing tools help you with the declarative model deploy machine learning models to Kubernetes really easily. But there are some caveats, and there were stars all on those previous slides. So let's just talk about this, right? Kubernetes may or may not be the right solution for you depending on the size. And so let's look at these lists. So first of all is scalability. Obviously, as I mentioned, Kubernetes scales really easily, and cloud vendors provide you tools with that. But management complexity increases with this scale, and you have to deal with balancing costs with the servers. With tools, amazing tools like BentoML, Kserve exist, you need to figure out whether you want to build your own thing versus buy or license some of these tools. These tool providers also have some managed services which you can use and get started easily, and that's, you need to check whether that is you can do that within your cluster or not. Tool provided CRDs are great to get started, but my personal experience is sometimes they get hard to debug. So if you have an MLOps tool that has an amazing community, I would lean towards picking that. One problem that I faced when deploying models with tool provided CRDs was in an air-gapped environment, which basically means that environment has no connection to the internet. The support system for doing that is not yet developed for Kubernetes. So one of those reasons why I decided to build my own container was something like this. And lastly, and this often get overlooked when you're talking about technology, but it's the people are using technology. And so look at your team. It takes a few months for your team to get comfortable with Kubernetes. And sometimes your organization might not be ready for Kubernetes. So with these caveats, I still feel that Kubernetes and machine learning ops on Kubernetes is the way to go. So this talk is going to be talking about or covering three things. One is we're going to talk about 3 ways to serve your model. We're going to talk about how do you build your own container and native Kubernetes operators for model serving. And then lastly, we're going to talk about how do you increase your deployment or model deployment velocity with CI/CD best practices like GitOps. Awesome. So let's talk first about 3 ways to serve your machine learning models. The first one is to serve a model as an HTTP endpoint. And this is what you see most common with even the tool vendors out there, right? Which is you containerize the model, in a server which is powered by an HTTP endpoint, either with Flask or Fast API. Really good options there. The way I think about serving these models with servers is HTTP endpoints is if the user is performing an action which is leading to a prediction, and then the user is waiting for the response back, this is a perfect place for you to insert that model as an HTTP endpoint. And response time 500 milliseconds is still very, very generous. You'd probably want something in the hundreds, in the lower hundreds of milliseconds, or even in tens milliseconds, as much as your network will allow. The second way to serve the model is with a message queue. So if the user action or a backend process, like let's say a file upload, which is an event source, triggers the model prediction, and there's no UI waiting for the response, message queue, a model working behind a message queue would be a great option. And so there's a model service which reads from the request queue and pushes its predictions either into a database which stores those predictions, or triggers another event. That's a great place for you to serve the model as a message queue. And lastly, the third way is long-running tasks that performs batch processing. So think about your nightly runs and predicting on a large amount of data where there's absolutely no user waiting for response. You can use something like batch prediction on using this third way, which is a long-running task. So let's compare these and see what options you have in each of these, right? In the HTTP endpoint, if you want to really build your own container and service for this, Flask, Fast API are great options. In fact, Fast API is going to give a talk tomorrow in real life, in the SF in real life event meetup for the MLOps community. I personally am using Falcon recently. Falcon 3.0 and onwards is super fast, and I prefer that. But each of these has some advantages that you should consider, which is fronted by Nginx and Gunicorn, which helps you make the model really stable. On the Kubernetes side, you can deploy this with primitives such as deployments and service, which we'll cover in a bit. But there are obviously great alternatives: Kserve, BentoML, Seldon, all amazing tools. Or you could do something with native or Knative, however you want to pronounce it. It's a serverless deployment on top of Kubernetes. With message queue, you can implement your own with Redis queues or Kafka or RabbitMQ, or pick a message queue that you want. If you need a very robust pipeline, I would highly recommend Kafka. But for the most part, just for triggers that are immediate, Redis, and that don't go over the RAM limit that your models, that your Redis has, Redis queues are a great option to do things fast. The Kubernetes primitives are just a deployment. You don't attach a service to it. There's no alternatives I know of in the tooling space which allow this. With batch processing, you can use your regular Python program fronted with a PM2 or a process manager to do it. The Kubernetes primitive would be a job, but you have some amazing tools, workflow tools that you can actually use for batch processing, like Metaflow, Flight, etc. Finally, on the inference graph, you'd probably be able to get away with the same tooling as above, but obviously tools like Kserve have inference graph, or Seldon has inference graphs, and you can use that to implement like more than one and so on. And as a director of data science at that organization, I needed to make sure that not just the technology selected was right, but the process itself was correct as well. And so if you have somebody new come in, or a new model come in that was just released with this amazing pace of AI that we're seeing, you want to move fast. And so the pros of build your own are: there's a consistent strategy, is operationally optimized, and works for all the three ways. With pros for the containerizing with the third party or easy container options are they're optimized. So some tools have micro batching that they allow, they scale down to zero. They have amazing advantages as well, so do look into it. The cons are most of them are HTTP endpoint only. If there is something is not working, it becomes really hard to debug, and you have to reach out to the actual authors of the open source project, which they have communities for. So you'd be you'd have some answers, but it might take some time. And lastly, with build your own, it's not as optimized as this, which is a con, but I still prefer it because it helps me deploy to air-gapped environments, and it's a standardized way for all three. The next few slides, I'm going to actually go into code, but if we don't want to look at all the code, on the left-hand side, you'll see some guiding factors, and we'll talk about how have it as a singleton. You have a load method, which will load the model once. You have a predict method, which takes just the input and the output. There's no HTML here, there's just no JSON here, it's just Python objects, which would be given to the model to predict, get the output, and return it back. I'm adding some performance counters here for my benefit to just check how fast these things are running. So that's the main class that has the model, but you need to package it in different ways for all the three ways we talked about. So for the first way, there are a few steps. The first is you need a health check for your service, HTTP endpoint, which Kubernetes can hit and confirm that the model is running or cycle it out if not needed. And for that, you need a health check handler. Again, for this, I'm just using Falcon because that's what I prefer these days. But Flask and Fast API are great choices as well. And so in the health check, you warm up the model. That's the first endpoint you need. The second endpoint you need is obviously your prediction one, where you have some additional logic to check if the inputs are correct or not, do the prediction, and then form your actual JSON object that you want to return to the user. And so this is kind of, again, Falcon's way of just converting dictionaries to JSON objects directly. So this is the second thing that you need to do. The third one is you need an app.py, which will connect these endpoints to the Falcon app. And that's basically what it has done. You have similar app.py with Flask if you've seen that code. But that basically defines at what route are we serving what endpoint. And in order to robustly serve this behind Nginx and Gunicon, we'll use the WSGI connector. So this is a specification that just says, hey, this is where the app is located. Great. So the fourth thing you need is the Nginx config. So Nginx allows you to add extra denial of service prevention, gzipping, and additional benefits that help you make sure that the model is not being misused, or at least put some security restrictions on the model based on it being open externally. Internally, or if you're using an external load balancer and external denial of service like Cloudflare or whatever it is, this might become less important, but I strongly recommend you do this because Gunicon recommends you do this as well. So you define that in the Nginx config that your Nginx server needs to talk to Gunicon. You tell it what is the port. Optional, you can provide some optimization like gzip, path protection, and so on. And lastly, the actual serve script, which starts both the Nginx process, it starts the Gunicon workers. You can define how many workers you want here, but I prefer just one and then scale up with the containers so that it's more stable. There's also, you need a way to handle sigterm events, because if the Kubernetes platform sends a sigterm event to the container, you want to stop all these services together. So that's way one. So with all of these 5 things in place, and I apologize that it looks complicated, but when it all comes together, you get a very robust server that can handle all the requests it can, and then you let Kubernetes orchestrator scale it up and down as needed. So for way 2, which is a message queue, we do things a little differently. The first thing you need is obviously the script that is reading off the queue. So you connect to your Redis or whatever queue you want, read the input topic and the output topic, load the model. From the topic, which is some serialized data, you will deserialize it. Here I'm loading it into JSON. You'll validate the input, you'll predict on it, and then send the prediction into the target or the prediction queue. So you're basically getting in messages about the requests for prediction from a queue, and you're passing the prediction requests to queue in this example. So that's a simple way in which you write your Python program. But the second thing you need here is your start script. I'm using PM2 as a package manager here. I'm sorry, as the process manager, which just spins up the workers and makes sure that if there is something that happens with the process and it fails, PM2 will start it back up and make sure that it's always running. So it just adds a layer of robustness in this process. So that's the second thing you do inside the container. Excuse me. For the third way, which is batch predict, you'll have another Python program wherein you're getting the path to the input and output files. And this can be on your S3 or some object store where you can download it inside the container, load the model, read from the files, and then either predict individually or as mini batches. Obviously, as predicting as batch makes it faster. And then you write it to the output file and store that file back into the object store. So that's the first thing you need to do, which is having this class that wraps our predictor. And then the second part you need is a script that starts this thing. So I'm just using Python here to start the process, but you can actually put this inside a shell script that you can call with a cron tab or cron job and say, this script needs to run midnight every night, and it will make sure that that happens. So those were how you containerize your model in 3 ways, but you need some additional sanity checks. And so unit tests are a great way to test software, and we'll just use the unit test package for testing our models as well. So we create a test wherein for some zero-shot prediction, like let's say this is just predicting whether this sentence is sad or happy, we assert whether the prediction is correct. And we also make some assertions on the scores returned, just to make sure that if the model version changes or if the underlying libraries change, the model is still good to go in production. So this is just a sanity check. This is not for the test curves that you're doing for model training, while model training or holdout data set. This is just making sure that from a product perspective, when you launch a model in serving, it passes all the checks. And to bring it all together in the container, you need an entry point script. Now, this entry point script will be a shell script, for example. We'll pass it a command, and the command will be either serve, test, start the message queue, or batch process. So you can see that in just one container, I have packaged the model and serving it in all 3 ways. And depending on the command that you send it, you can start it as a HTTP endpoint, a message queue, or a batch process. And that makes it very convenient, because now you don't have to create different ways of serving for 3 different things. If somebody new joins your team, they are aware of how do you containerize, and they can learn quickly and repeat the process. So operationally, this is a very sound method. Every container has a Docker file which has the instructions on how do you create the container. And think of it like installation instructions as a non-root user. So here you can see that we created the non-root user and made sure it can own the Nginx and the folders that we will load the models in. And we also pip install all the requirements that our models need. The second part of this file is more interesting, wherein I prefer to download the model inside the container so that when the model server starts, it has the model right there at a path. And so inside this build command for the Docker, you can see that for the zero-shot classification, I am downloading using Hugging Face Transformers library, the model itself. And I think that makes it super fast, because you don't have to load the model at runtime. But obviously, if your model is, let's say, tens of gigabytes, you might need to consider a different strategy. I prefer to also add linting and MyPy to my code, because every check-in I make, we just ensure that there are there's enough sanity check on the code itself that makes the model really good. And finally, you mention what the entry point is and how to run it, so that when we run the serve command or when we run the start message queue command, it knows where to find it. A lot of people with their MLOps pipelines also store their models in a model repository, right, or model store. And what I've found to be useful is to split your your Docker file into a two-stage process. In the download stage, you will, for example, use MLflow, where your model is stored, and you will download that model into the container being built over here in the download stage. And in the production stage, which we saw in the previous Docker file, what we'll change instead is, instead of downloading it from Hugging Face, we will copy the model and the requirements from the download stage into the production stage. This kind of a two-stage strategy is also used for when you're building front-end apps or when you're building Java apps, but it also helps you build and containerize your models. One important point, never put passwords or access tokens inside this. You can use something called args to do it. So this I found to be super interesting way of getting the model inside the container. So I'll take a pause here, which just and summarize what we've just seen. So there are three ways to build your own containers. One is you serve your model with an HTTP endpoint. The second one is you serve your model as a message queue. And third is you serve your model as a batch processing. You use, I prefer that we use HTTP endpoint if a user is waiting on the model prediction right away. If you can allow for some delay for the model to predict stuff, you can use a message queue if there is an event-based mechanism you have that can handle it. And this allows for you to act on a large amount of data in a scheduled fashion, so say nightly or something. Containers wise, the core of the container is the program, the main class which has it, but then for each of the three ways, you have some additional files that help you package it together. And then finally, you create the Docker file, which creates your container and pushes it to repo. Awesome. We're now going to be changing gears and see what continuous integration looks like. So what is exactly this whole CI/CD thing you heard of? And some of you might already be aware of this, so I apologize if this is redundant. In order to increase the velocity of how you deliver software, the software engineering community has come up with ways in which you don't have release cycles of like 1 month long release cycles. Instead, what's emerged as a best practice is to allow people to perform continuous integration of their code and then continuously deliver that service into production. We're going to be using a newer way of doing CI/CD called GitOps, which has been widely used in the Kubernetes community, or at least people who are deploying apps on Kubernetes. There are other ways to do it, but I think for the purposes of this talk, this is a straightforward way in which, when you decide that you want to either bring your own container or you want to use third-party tools like PentoML, Kserve, and Seldon and the likes, you can perform CI/CD in the same way. So the containerization part is separate from this CI/CD part. So let's look at how this works. The ML engineer, she comes in and she has the code, which we just saw, the whole container code, and that's pushed into GitHub or any Git repo. Obviously, GitLab and other vendors exists. And you have your model, which might be stored in the model store from your data scientist, right? And so the first step is when you do this Git commit, CI processes like GitHub Actions or Circle CI or GitLab has its own way of doing things, will run a process that can help you build the container. So they will just run the Docker file for you and build the container using the instructions we have in the Docker file, and then push that repo, the container, inside a container registry or the repo for that container. So that's the step one, which is from the code or the model, anytime a new code or new model becomes available, using a pull request, it automatically gets containerized and it automatically gets pushed into the repo. So that makes these steps over here on the right-hand side very automated. The second step is the continuous delivery step, which we will talk in a bit, but that helps you actually deploy this container that you've just created onto Kubernetes. So I'll talk about that in a bit. So the first step that you need for your continuous integration is to have some sort of a script that just helps the CI tools find what to do. And I've preferred Docker Compose, learned it from some of the best people I've worked with in my previous companies, where you have this Docker Compose file can be used both for development locally on your machine as well as have a test target, which the CI software will use. One advantage of using Docker Compose is, let's say your model depends on a database, or your model depends on some config file in S3, right? And you need to load that somehow. So specifying in Docker Compose all the temporary services that your model depends on, loading those up and etc., creates a very complete package of your model service only for the purposes of for testing and for the CI. Obviously, Docker Swarm is a way to deploy models, and Docker Compose is used there somehow. But I'd say that in my experience, I prefer to use Docker Compose for developing locally and for running my CI processes. Here you can see we have a service target which spins up the container and serves it as a local host, and that's how I use to test out whether what I've coded locally works or not. The second thing you need is to specify what happens on a pull request. So what we're going to say is create a file in the GitHub .github folder, which says do this on a pull request. So if there's a pull request on the branch main, this defines what you need to do. And here what we're saying is check out the code from the repo. So it'll download the code from GitHub on that particular pull request, and then run the tests inside the container for that particular branch. So this is just specifying like, great, this is how you run that CI process as step. What this allows you to do is add some, so in addition to